work has to be done by external. So this source charge is kept fixed and another test charge has to be brought from anywhere to this point. Then in order to bring that test charge to point P, we have to do work. And that much work done will be stored in this test charge at point P. And if you want to test it, that whether work has been stored as energy in the test charge, you will realize it after releasing the test charge. As soon as after bringing the test charge Q from anywhere to this point, you release it, you will see that this test charge small q will move on its own away from this fixed source charge. How it is possible? That nothing can move without any on its own without giving any kind of energy to it. So here, after releasing this test charge at point P, it will move away on its own and will continue to move until the repulsive force acting on this test charge becomes zero. So this repulsive force will be zero at infinity. That's why we, in order to define electric potential, we take one of the points at infinity and while other point P in the field of this force charge. I think that this is given in your textbook. That's why I have selected this one. So we must start from here. And more or less, many things was discussed in the last class, electric potential. So this is the basic about that one. Okay. So if one bring this charge to point P and hold it, if you don't hold it, it will not be situated at point P, but it will move away from this fixed source charge and will move to infinity. So in order to bring that test charge, the work done by external effort or agent is stored as potential energy in that test charge. In the same way as you take a ball from the surface of the earth to any height, and after that you release the ball will not be there at that point where you have taken to, but it will come down on its own. How? Why it will come down? No force is acting on it. No one has pushed it down. Still it will come down. Why? It means while you were taking the ball to that height, you have done a work by your force, by applying muscular force. And that work has gone where? That work has transformed into a kind of energy that is stored in that ball. So after releasing that ball, now that ball will come down with increasing kinetic energy. So who impart kinetic energy to that ball? It's a miracle. No one is pushing, no force is applying on that ball. Still, its kinetic energy getting increased. It means the amount of work that you have done while you taking the ball to a height, that work done is stored as a kind of energy due to position of ball from the surface of the earth. And that kind of energy that was stored in the ball and can be used for future purpose now. So as soon as you drop the ball, release the ball will come down on its own. And remember, if ball is at some higher location, so it will strike the ground with higher kinetic energy. If ball is dropped from lower height, then it will strike the ground with lower kinetic energy. It means That much amount of work done on in bringing the ball to a height edge, the same amount of energy will be transformed into kinetic energy after releasing. So same case is here. When you bring this charge, this charge Q from infinity to this point P, whatever amount of work you have done will get stored as a kind of energy, and that kind of energy will be called potential energy. But here is not earth, not mass. Mass is not taken into account while describing this interaction. So we don't care about the gravitational potential energy. It means there must be another kind of potential. So here, as interaction is taking place between two charge, not between two mass. Therefore, whatever energy is stored in this test charge when brought to point P is electric potential energy. And look at this energy will change if location or position of this test charge changes from point P to somewhere else. From point P to here, or from here to here, from P to Q and P to R. If you take at point P, its potential will be higher because it is closer to the source charge. Because source charge will repel with a stronger force. So external agent have to apply a stronger force to overcome this repulsive force. So much more work will be done at point P in comparison to at point R, because point R is away from the source charge. So here less repulsive force will be there. So less work has to be done by external agent. So potential energy at this point will be less in comparison. So what we have learned from this one. So configuration or arrangement of charge from the fixed source charge causes a certain kind of energy. That energy is called electric potential energy. Remember, potential energy, a kind of energy that can be stored and can be used in future. So as you take the bricks to a height h, to a height of roof, and put there that bricks, and bricks will be there on the roof. No one is knowing that this brick has capacity to do work. So one can realize when this brick dropped from the roof, and while coming down, if someone is standing there, this brick will strike with his head, and then he will realize that this brick has capacity to do work. So you know that energy is defined as capacity to do work. So brick that was put on the roof after releasing from the roof can break anything while coming on its way, can change the shape and size of the object with which it will strike or collide. It means energy was stored in that bricks and can be used for future purpose. The same thing you do, you use electrical energy to take water to the height of roof in the tank, water tank. Why did you, why you take the water to that height? Because using electrical energy, you transform electrical energy into gravitational potential energy, because every time, all the time, electricity will not be present there. So you transform that electrical energy into gravitational potential energy, taking the water to the tank, which is placed at the top of the roof from the surface of the earth. There it could be some height h. It means water stored in the tank will have some kind of energy in it. And now switch off the electric motor, cut the supply of water into the tank. And when you open the valve of null tap in your washroom, you see that water is coming down on its own. No power is needed. So how? Because you know well that Newton's law suggests that nothing can uh, change its position or a state of rest or a state of motion on its own until and unless some external effort is applied. So here water comes down on its own. Why? There must be some kind of energy stored in water. That's why we say that potential energy, a kind of energy that can be stored for future purpose. As you earn money and put into the bank account and earn, and whenever you are in urgent need, then you take out this money. So earned money can be stored for future use. In the same way, certain kind of energy can be stored for future use. Therefore, electric potential energy is that. Now let us check out. So far we have discussed that while bringing a test charge Q from infinity to a point near about the source charge, we have to do work against repulsive electrical force, and that work done is stored as electric potential energy. So in this chapter, we will discuss all these are given in this case. So for this one, we take a small displacement dr, and then we calculate amount of work done in displacing this test charge against electric field or against electrical repulsive force. Then work done can be dW. So work done can be dW, and dW can be expressed as external force displacement, a scalar product of external force into displacement. One more thing to be remembered, that while bringing this charge, test charge, from infinity to point P, one has to be careful that this test charge must not bring so fast, must not bring so fast, because if you bring it fast, briskly, then this test charge will have two kinds of energy, kinetic energy as well as electrical potential. But here we are going to test only electric potential energy, so we must ignore kinetic. So in order to ignore kinetic energy of the test charge while bringing from infinity to a point in the vicinity of field of source charge, we have to be cautious that while bringing the charge, it must be brought slowly. So as you bring it slowly, its kinetic energy becomes negligible and only potential energy becomes dominant. That's why in order to define electric potential or potential energy, you must say that amount of work done in bringing unit positive charge from infinity to a point in the vicinity of source charge slowly. Amount of work done in moving a test charge from infinity to a point in the vicinity of source charge slowly. So therefore, we have discussed about that. It must be brought slow. Now, a small amount of work done by external force is given as F external dot dr. Dr is the displacement. So remember here, external force is applied in this direction and displacement is also in this direction. So work done by external force will be positive. On the other hand, work done by electric repulsive force will be negative because electric repulsive force is in this direction. So angle between electric repulsive force is 180 degrees. So we integrate dW equal to F dot dr. Now integrate because we are moving the charge from R to P. So we write here from R to P. So upper limit is P and lower limit is R. So you replace external force by electrical force because in equilibrium, net sum of force, external and electrical will be zero. So external force applied onto the test charge while bringing from infinity to point P or while bringing from R to P must be zero. So external force is just equal to opposite of that of electric force. From here, in figure, you can say electric force will be directed in this direction and external force will be directed in this direction. So here, in place of external force, we place negative electric force here. So work done is negative here. So this work done is against electrostatic repulsive force and get stored as potential energy. And you will remember that at every point in electric field, a particle with charge Q possesses a certain electrostatic potential. While bringing it from infinity to point P, everywhere on the way, this charge Q, a small q, will have certain amount of energy associated with it. Only energy of this charge will be zero at infinity. That's why while defining electric potential or potential energy, we take one of the point at infinity. Okay, so this work done increases as one move towards the source charge because as one move towards the source charge, repulsive force also increases. So work done increases, so potential energy also increases as one coming closer and closer to the source charge or fixed source charge. Okay, so we can say that work done increases its potential energy by an amount equal to potential energy difference between the 2 points. Here we are taking 2 points P and R. So amount of work done while bringing the charge Q from infinity to R and while bringing the charge Q from infinity to P will be different because this charge is away from the source charge. So here will be less repulsive force and here will be more repulsive force. So while bringing the charge from R to P, it is just equal to amount of work done. From R to P is just equal to potential energy, difference of potential energy between R and P. So difference in potential energy can be expressed as, say, potential energy at P is UP and at R is UR. So difference between the two potential energy is equal to amount of work done in moving the charge Q, small q, from R to P. This is the basic things. Then I will take to the previous lecture. So this was the just introduction. One point more that you have to remember that Therefore, we can define electric potential difference between 2 points as work required to be done by an external force in moving charge q from one point to another point. Without accelerating here, word very important. I say you not only without accelerating, but slowly. So while you moving the object very slowly, acceleration automatically becomes zero. So this word is important here to write in definition because you are in this class, 12th class, not in class 10. So you must write that slowly. A charge when brought from infinity to a point slowly, then amount of work done. Bringing that much charge from infinity to a point is stored as electric potential. So two important comments may be made at this stage. What? Right side of the equation uh, 2, 2.2. This is the equation. This is LHS in the left hand side, change in potential energy. And right side, amount of work done. So amount of work done while moving the charge, a small q, from R to P is just equal to change in potential energy. Okay. Now, here we have to recall once again that depends only on the initial and final position of the charge. Remember, amount of work done while bringing the test charge from R to P only depends on initial position and final position, but it does not depend on the path through which the charge Q is brought from R to P. So this must be kept in mind that amount of work done between from one point to another point in electric field is independent of path followed, but only depends on initial and final position of the charge. So it means that work done by the electrostatic field, work done by an electric field in a moving charge from one point to another point depends only on initial and final points and independent of the path taken to go from one point to another point. This is the fundamental characteristics of conservative force. That's why we can say that electric force is a conservative force because potential is always associated with conservative field. Gravitational field was conservative, so potential was conservative. Now electric field is also conservative. And similarly, magnetic field is conservative. So here we have to keep in mind that points because you just see that your NCRT textbook has much more adequate information given in brief language, so you must follow this one. And then I will go to the mathematical derivation. The path independence of work done by electrostatic field can be proved using the Coulomb's law. Here we don't need to discuss. So now check out this activity that this para you have to go through. I don't need to discuss here, but you can ask me questions of that. So now let us move here. This is the question that while taking the charge Q, following various paths, following this way and following this way and this way and this way, the amount of work done will remain same. That is UP minus UR equal to WPR. So it means that it depends only initial and final position. Now next thing is that. So the qualifying remarks made earlier regarding the potential energy also apply to the definition of potential. To obtain work done per unit test charge, uh, uh, we take an infinitesimally small charge that is called test charge and obtain work done due to bringing through a small distance dr, and after that one you have to integrate this. So here the question topic is potential due to a point charge. First of all, in the last class we have just discussed that electric potential is defined as amount of work done in moving unit positive charge from infinity to that point. So that was all clear for you. Now here, uh, first topic is that we have to calculate electric potential due to point charge. Look at, this is the point charge, Q, and which is kept fixed here, which is kept fixed here. And at a distance r from this charge Q, and the point is named as O, there is another point P. There is another point P where we have to calculate electric potential. So it means that we bring a test charge Q, a small q, from infinity. This dotted line indicates that you are bringing that test charge from infinity to point P. So amount of work done in bringing a small test charge or unit charge from infinity to point P is called electric potential at point P. So now we take a small displacement dr, differential displacement dr. So at this distance, repulsive force will be in this direction, but force applied by external force is in this direction. So amount of work done by external force or negative of electrical force will store as electric potential energy. So at this point, at a distance of r, electric field is given as kq by rq, unit vector r. अभी तक आपने पढ़ा है के क्यू बाय आर स्क्वायर, लेकिन यहाँ पर हम यूनिट वेक्टर से मल्टीप्लाई कर दिए, इसलिए यहाँ आर क्यू लिखना पड़ेगा, बिकॉज आर कैप इक्वल टू वेक्टर आर डिवाइडेड बाय मैग्नीट्यूड ऑफ आर. तो अब ये आप इतना तक आप समझ गए हो. अब हम आगे बढ़ते हैं, अब इसको इस लैंग्वेज को आगे हम नहीं फॉलो करते हैं. सो फार यहाँ हमने देखा है कि इलेक्ट्रिक पोटेंशियल इज इनवर्सली प्रोपोर्शनल टू डिस्टेंस, जबकि इलेक्ट्रिक फील्ड वाज इनवर्सली प्रोपोर्शनल टू स्क्वायर ऑफ डिस्टेंस. जरा ध्यान दीजिए, दिस इज द इलेक्ट्रिक फील्ड एट ए डिस्टेंस r from the source. So amount of work done is obtained here, and after that we integrate it. Integration का लिमिट हो जाएगा, लोअर लिमिट हो जाएगा इंफिनिटी, क्योंकि इंफिनिटी से ला रहे हैं. अपर लिमिट हो जाएगा, कहाँ तक लाए हैं, अप टू r. तो r हो गया. इंटीग्रेट करने के बाद हमारा रिजल्ट ये मिला. दिस इज द वेल नोन एक्सप्रेशन फॉर इलेक्ट्रिक पोटेंशियल. So this potential can be expressed as kq by r. It means electric potential is directly proportional to source charge and inversely proportional to distance from the source charge. देखिए, electric field was directly proportional to source charge and inversely proportional to a square of distance. So here, if you plot the graph representing electric potential and electric field on the same graph, you will see that electric field, graph representing electric field, will be more deeper than graph representing electric potential. Why? Because electric potential vary inversely as a distance, and electric field vary inversely as a square of distance. Therefore, this graph must be kept in mind. Okay, now we have to move on the next. Okay, so we have to. Now time is about to be. Let me check. Okay. All right. इसके बाद मैं